results here, which I will be presenting. It's a research done by master student Jakub Bębenek. And for what it is related, this results here, which we are doing, this research is related to quantum networks. I mean, what we are interested here is the creation of long-range coherence and entanglement. And of course, you see how it could be done simply taking some qubits or modes, and by suitable coupling them, you can create long-range coherence or entanglement. Question is how? I mean, in laboratories, we have two possible couplings available. This is what we call linear coupling. It is photon exchange coupling under this name, or beam splitter type coupling. And this kind of coupling is now, it cannot create entanglement between modes, but can create coherence. And there is another possible coupling applied. It is what we call nonlinear coupling, which is two photon exchange coupling, parametric interaction, parametric down conversion type coupling. And this is known that this kind of coupling can create entanglement between the modes here. So you see, things maybe look very simple, that you can think, okay, if I want create long-range coherence, then I can apply linear couplings between all of these modes here, so I will get a long-range coherence. If I want long-range entanglement, then I will apply nonlinear coupling between each of these modes here, and I will get a long-range entanglement. But in fact, you see, things are not so simple. I mean, studies of just simple chain, short chain, involving three here qubits or three modes, they show that, for example, if you apply nonlinear coupling between modes N and B, you create, of course, entanglement. And if you apply nonlinear coupling between B and C, you create, of course, entanglement between B and C. But then it's a question, what is the correlation between A and C? I mean, A and C are entangled or they are coherent? And this results here in these papers, they show that A and C are coherent. If A and B is entangled and B and C is entangled, then A and C is coherent. And reverse situation. If we apply nonlinear coupling between A and B, we create entanglement. Between B and C, we apply linear coupling, we create coherence. Question is, what is a correlation between A and C? The answer is the entangled. So you see, applying here couplings to create long-range coherence on the entanglement, even on this simple short chains, is not easy to predict. And so today I will show you even simple situation when we have two modes, and we will study here what kind of correlations, I mean, coherence or entanglement we will create, how it depends on the coupling. No, I already said how it depends on coupling, but also it depends on the state in which these two modes are prepared. So what I mean, we will assume that modes, they are somehow populated. So population are expressed by these correlation functions. Also, they can contain two photon correlations. I mean, they can be in squeeze states. And what we are interested in, how different kind of decoupling, linear, nonlinear, can create this correlation function, which is known as a first order coherence. This function creates coherence between. If it's non-zero, it means that modes are at least partially coherent. And this two photon correlation function is responsible for entanglement. In fact, what we will be here presenting, not this correlation function, but mostly we will be interested in the ratios, because this ratio between two photon single mode correlations and normalized to the population, it distinguish between classical and quantum correlation contained in the modes. So we will look at how presence of the classical or quantum correlations in the modes influence on the creation of these two correlation functions for different kind of couplings. And normalized this function is well known in physics, is the coherence function. And that one is a degree of coherence, or is defined here. It also can be used to distinguish between classically correlated or quantum correlated modes. Whether we have entanglement or not, there is a threshold, value when this correlation, the ratio is larger than one. We say that modes could be coherent. If it's smaller than one, they are classically correlated. And how this correlation function distinguish between classical and quantum correlation is just simply look at the variances of quadratic components of the single modes. And you see here that this, if say that there are correlations in the modes to some amount of m, the degree of correlations to the number of photons is m over n. So if classically we can correlate photons in single mode to the level of number of photons. So you see that classically we can make maximally eta AA equal 1. So which means that we can, of course, get asymmetric distribution of the noise, but we cannot beat the quantum limit. Quantum limit here for fluctuation is half. So if we reduce fluctuations in one of these two quadratures below half, we say that we have quantum correlation. So quantum squeezing. So when we have a quantum field, you see with quantum field we can achieve amount of correlation larger than n, which is given here by this relation. And so go to our situation that we have two modes, and which could be first, we will consider two situations that modes could be, both modes could be in equally squeezed states, so contain the same number of photons and will be squeezed to the same degree of m. And another example that one of the modes is squeezed, another one is vacuum. And then we will see how we can correlate these two modes in these two different situations. Now, first with linear coupling, okay? With linear coupling. And so look at the first situation that we have what I say an input, that we have two modes which have the same number of photons. The correlations are to the same degree. What is an output? An output, here what we do calculation in this way, that simply from this Hamiltonian we find equation of motion in the Heisenberg-Langevin equations for motion for A and B. We here allows the damping and losses, and then find the time evolution and calculate the averages. So I skip this mathematics because of short time, but here these are the results that you see. If an input we had two modes with the same number of photons, on output number of photons is conserved here. There is no first order coherence, which means that this linear coupling here, when you have two modes which have the same number of photons, you cannot create coherence between these two modes. But if you have two photon correlations inside the modes, you can create two photon correlations. You can entangle these two modes if there are some two photon correlations present inside this mode initially, but not always. There is one quite strong conditions that you see you can do it only when the sine angle of this, we allow that these two error ellipses can be oriented in different way, that there could be phase difference between them. You see that if these two ellipses are equally oriented, that we have completely identical modes, that we can not distinguish which mode is which one. You see what is the effect that linear coupling won't couple to this mode, won't create any correlation. There must be some difference between these two modes in order to get the linear coupling to create correlation between the modes. I mean, at least you see here these two ellipses must be oriented in different directions. Yeah, and now it's a question. No. So how? I mean, interesting question. How the correlations here between the modes are created? I mean, we very often do this way that we apply interaction and calculate correlation, say, oh, we've got that everything is correlated. But how many of you ever thought about how it is done? I mean, what is important? What quantity, what should happen in the system in order to create correlations? And here it's easy to see. You see that compare it how internal mode correlations are changing with the coupling strength, and how the intermode correlation, two photon correlations are changing with the coupling strength. Phi contains the coupling strength G. Comparing this one, you see that simply intermode two photon correlations are created due to variation of the correlation inside the mode with the coupling strength. So which means that correlations inside the mode must vary. When they are varied, then you can create correlations here. So you see, these correlations are responsible for entanglement. So if there are some non-classical correlations present inside the modes, you see creation of entanglement is not a transfer. Sometimes people say that there is a transfer correlation from the modes to between the modes, but this expression is showing it's not true. I mean that these correlations between the modes are created due to change, that they must change here. And what is interesting here, that number of photons is conserved. So we have here example of creation correlations between the modes without exchanging photons. So we can entangle two modes without exchanging photons. And here you see, this is the picture here, that simply when correlation with coupling strength are decreasing inside the modes, correlation between modes are increasing. So you see maximum we get and the interflection of this curve, when this curve is changing slope from dying to saturating. And the same happened here. These two pictures show the quantum regime, classical regime correlation, that this is true for both if there are classical correlations inside or quantum correlations inside. And now, the second case oh, we time finish. Oh, okay. So maybe I will finish this part only. The second case, when one mode is vacuum mode. Here we have a different story. Here we have a real transfer of population from one mode to another mode. And also we have a transfer of correlations from one mode to another mode. And again, due to the transfer of the population, first order coherence is induced. And due to transfer correlation, second order coherence is induced. So what we have here is that simultaneously we create entanglement and coherence between these two modes. And you see, again, it is created due to the transfer. So again, these correlations function between the modes are due to variation of population and correlation inside the modes. So what left is this nonlinear case, but my time is finished. So maybe, okay, I won't keep you for coffee break. So if you want to learn about this nonlinear case, you can find this on ICAF. Thank you. Sorry.
Okay, Zbigniew, thank you so much for an interesting talk. Maybe we have some questions. We have some time still for several questions. Okay. Maybe this question will be related to non-linearity.
Okay.
Yeah.
Thank you for the talk. My question maybe is not totally related, but maybe you can give some intuition. So when you create entanglement from two squeezed states, the best is to have them cross the orthogonal squeezing, right? To have maximal entanglement.
Yeah.
But then to disentangle them back, you can have like arbitrary phase add into one of the.
What you mean get back?
So they have two modes squeeze entangled.
Yeah,
Slide.
you have. I mean, you have two modes which are saying for linear coupling you need them to be to maximum correlation. They have to be orthogonal to each other, right? And what interaction is doing is transferring correlations from one to another, turning the squeeze modes into thermal states. I mean, what linear coupling is doing with two modes is always turning them into to be equal. This is what is seen here, that you see when they are in thermal state, there are no any correlations. So linear coupling has this tendency, if there are some initially correlations present inside the modes, very strong coupling leaves these modes completely uncorrelated. Zero correlation inside the modes, zero correlations in between. Non-linear is opposite. I mean, I didn't have the time to talk, but I just show you that here we have an opposite situation, that here nonlinear coupling, of course, is turning them into, is turning the modes to be highly coherent. You see, the degree of coherence is 1 when the coupling is strong, but still leaves some correlations, classical correlations. So with nonlinear coupling, in strong nonlinear coupling, you get modes which will be left in classically correlated, but maximally coherent. It's completely reverse situation. I'm sorry, I didn't have the time to tell
I'll ask
and compare it.
during the coffee break.
But just to summarize that nonlinear coupling is reverse what linear coupling is doing.
Okay, the next question.
Hi, thank you for a very interesting talk. My question is related to what you mentioned in the beginning of the talk, that the coherences and entanglements, I'm here, depends not only on the coupling, but the kind of states that you have as well.
That's right, exactly.
So what if we open up the range of states we have to play with? So for instance, cat states or very exotic kind of
exactly, but I forgot to say this Gaussian systems. I
yes.
use the Gaussian.
So, for instance, in other systems like things I work with, I have access to these other kind of
systems.
Yes.
You can.
So, do you have some intuition on when we introduce non-Gaussianity, what signatures might emerge, or in more or less prominent ways?
Of course, for non-Gaussian states, you have much more possibilities to prepare modes than with Gaussian, because Gaussian you can only populate and two-photon correlations, nothing else, right?
But do you have some, say, intuition or on what kind of non-Gaussian states would be most interesting to look into?
No.
Okay, thank you.
I don't know what kind of could work here to create long-range coherence or long-range entanglement. No idea, sorry.
Thank you, no problem.
No, I haven't thought about it, sorry.
Any additional questions? Yeah, so if you summarize, intermode correlation and generation of them strongly depends on coupling strength. It influences it. Intermode generation of correlations.
I mean, we have results up to five modes, 5 qubits at this moment.
Okay, nice.
As I show you, there are complications on the level of 2. Yeah, if you go to 3, behavior is completely not related to that one what you found for 2. So everything is changing if you increase the number. So everything requires separate studies.
So a lot of work ahead.
Yeah,
Let's thank again for our speaker.
Thank you.
Yeah.